let's say that you have a plot of f of x as a function of x, and you're only given certain points. The crosses are known points, right? So you did an experiment, let's say, and then you measured some data, f of x, as a function of x, but you only have access to those 4 data points. You're asked to compute f dash x at some unknown point. So let's say this point, you need to know what f dash x is. So how can you compute the derivative at a point at which you do not have any measurements, right? Or even for that matter, how would you compute the derivative at this point? Okay, you do not have measurements at that point. Right? You have a measurement at that point, but you don't have many measurement close to that point. In order to compute the derivative, uh, you basically need to be able to compute f of x plus delta x, f of x minus delta x sometimes, and so on, right? So the idea here is, if you have data like this from an experiment, say, what you can do is you can fit a curve which passes through all these points, okay? And then you see that uh, if you know the curve, which you can do by curve fitting, then it's sort of easy to compute f dash x, because now you have an analytical formula for f of x as a function of x. And f dash x is just taking the derivative of that function and evaluating at a point. Okay, so that's the idea here. So what we do here is, one, we notice that there are 4 points. There are 4 points given. That is x, fx1, x2, fx2, so on till x4. Well, this is 4 points. Let me just write all of them down. x3, f of x3, x4, f of x4. Okay, so if there are 4 points, then you can ask, what is the minimal order polynomial which will pass through 4 points? And the answer is a third order polynomial will pass through 4 points. Okay, what does that polynomial look like? Well, it's approximating f of x. So f of x is a0 plus a1x plus a2x square plus a3x cube. So you see that there is a polynomial with 4 unknowns, a0, a1, a2, and a3. Now we solve for a0, a1, a2, a3, and we call this 1. Using 1. And then once we have computed a0, a1, a2, a3, we can then evaluate f of x at any point. We can also evaluate f dash x, which is simply a1 plus 2a2x plus 3a3x square. And so now we have a formula, analytical formula for f dash x. So this is the idea behind the polynomial representation. You curve fit the points with a approximate order polynomial. You usually go for a low order polynomial, minimal order polynomial, and then find the constants and then evaluate the function by taking derivative. Here you can, the nice thing is you could find the first derivative, you could find the second derivative, you could also find the third derivative. Okay, so let's put this into action. Let's solve a problem. So the problem is, so example, the value of f of x at x equals 0, 1, 2 are minus, oh, sorry, 2 minus 1 minus 2. Okay. Compute f dash at x equals 0.5. Okay, so we are given here just 3 points. So the curve passes through 3 points, and I'll put those points here. So we need to write them as pairs x, f of x. So those pairs are x is 0 and 2. So when you put f of 0, you get 2. Okay, next one, if you put x equals 1, you get minus 1. And last, if you put x equals 2, you get minus 2. So 3 points. We ask ourselves, what's the minimum order polynomial which passes through 3 points? Well, it's a second order polynomial, because the second order polynomial will have 3 constants. Choose so the polynomial is f of x equals a0 plus a1x plus a2x square. Next, we substitute the value, those 3 values. So we have, first we have x is 0. So a0 plus a1 0 plus a2 0 equals a value of 2. So it's clear from here that a0 is 2. Next, we put a value of 1. So a0 plus a1 times 1 plus a2 times 1 equals, it's minus. So we have minus 1 equals, well, a0 is 2, a1 plus a2. So we have a equation for, we can't solve for both these constants in one equation. So we just write down an equation here. So minus 3. Okay, and the last value is when x equals 2, f of x is minus 2. So I put 2, a1 times 2 plus a2 times 2 square, and then we saw the value was minus 2. Okay, so that gives me minus 2. A0 we figured out was already 2. So 2 times A1 plus 4 times A2. So we can write, well, equation twice A1 plus 4 times A2 equals, we move this 2 on the other side, we have minus 4. I can do a little bit more simplification. I can divide this whole expression divided by 2 to get A1 plus 2A2 equals minus 2. Okay, so we have 2 equations and 2 unknowns. So I'm going to write those equations down. So this is one equation. Let's call that number 2. And then this is 3. So okay, so that's a way to compute the derivative when you're given some information about the curve, but not really the curve, right? And this is very handy because when you do experiments, you typically have data at discrete points, but you need to compute things like derivative. This is one way to do it. Okay, what we have seen so far is what is known as the complete derivative. If you're given a function y as a function of x, you can find y prime. One of the things about some of the applications areas of in mechanical engineering is that there are situations where you have partial derivatives. You have things which vary as a function of x and y. So partial derivatives are also important. In fact, when you do FEM, finite element analysis, it's basically computing, say, heat flux as a function of the boundaries of a plate. That would be a function of x and y. So you need to be able to do that. So let's look at how to compute partial derivatives. It's actually a simpler idea. Just take what you do in one dimension and extend it to 2 dimensions. I will not really solve a problem, but give you some, I'll give you the equations and then I'll give you homework problems where you'll test this on. So the next thing is partial derivatives. Okay, so here we're looking at functions that depend on more than one variable. They could depend on more than 2 also. So e.g. f of x comma y. Okay, so let's assume that we want to compute uh, df dx. So you see that there's a partial f, partial x. That means that that basically means that f is not just a function of x, but it's a function of x and something else. If it was only a function of x, then that partial, the symbol, would be replaced with the d, right? Just like we've done before. So when you compute df partial derivative of f with respect to x, you hold y equal to constant. Okay, so you assume that y is constant, and that's how you take the partial derivative. Just to give you an example, if f of x comma y is x squared times y, and if you're told to compute the partial derivative of f with respect to x, the rule is that you hold y constant. You treat it like a number. Okay, when it's a number, you don't really take its derivative. So here you need to take the derivative of x squared, which is 2x, and y is a constant, so it's y. And then if you want to compute df dy, you do the exact reverse, which is you hold x constant and take the derivative with respect to y. So here, x squared is a constant, and the derivative of y with respect to y is just 1. So this would be your partial derivatives df dx when the function is given analytical formula. Okay? So that's how you do it analytically, but here we're interested in doing it numerically. So what we do here is we assume that what I'm going to do is I'm going to assume that you're trying to compute uh, the partial derivative at a point xi yj. We'll write this as f of I comma j, and the reason why we'll do it is because you'll see that if you start writing f in brackets xy, it's just going to be take a lot of space, and just it's a nice notation to make this make the writing very short and succinct. So let's assume that that's how we'll denote the function f, which is a function of I and j. You could actually go to kl, whatever you want, just put I, j, kl, so on. But let's just focus on 2 dimensions in this course. So if that is the case, then I'm going to write a few formulas down. Let's look at the first derivative. So forward difference. Okay, so here we're interested in computing df dx. Okay, and then let's say it's at I comma j, that is xi and yj. So the rule is you hold y as a constant and then take the derivative of f. This is very similar to what we have done in the past for the forward difference. What we do here is we take f of I plus 1, subtract from f of I, and divided by delta x, right? This is for 1 dimensions. If you had only 1 dimension, you do that. But since the second dimension is a constant, you just have to keep it as it is. So j. So similarly, if you want to compute df dy at x of ij, then it is f of, so j plus 1 minus f of j, and then I is constant, so just keep it as it is, divided by delta y. Okay, let's look at backward difference. Okay, just put a note here. So f of I plus 1j is nothing but f of xi plus delta x yj. Okay, and then you can do a similar thing for the index j. That's what it means to be I plus 1 comma j. Okay, so here's the formula for the backward difference. For the backward difference, you have fi comma j minus f of I minus 1j divided by delta x, and then df dy I comma j is f of I j minus of I j minus 1 delta y. Okay, so I will not write it down, but when I say f of I minus 1, that would mean x minus delta x, xi minus delta x. Okay, two more. Let's look at the central difference and then the second order second derivative.